Made on web work, you guys will know which problem number and I won't remember. It's 4 or 5 or something. When you have a sum of two iterated integrals in 2 dimensions, 5, and it says evaluate without any untoward methods of integration, what does that mean?
So you use inverse hyperbolic sine functions.
Or trig substitutions.
Right.
What do I want you to do?
Wolfram alpha.
Figure out the local. It ends up canceling, so.
No, I don't want that. How do I want you to do the
this
problem?
while we were practicing.
Well, I know you know because I gave it to you in office hours. What's the whole point of the flexibility you have with double integrals or triple integrals that you do not have with single
That's
integrals?
what I'm saying. If you switch it around, it'll cancel, and then you don't have to worry about the.
What do you mean?
So you have to switch it around.
You have to.
Yeah.
So what I'm asking you to do is change the order of integration. Draw the region and set it up as one iterated integral.
I don't know if I did that.
The whole point is draw the region, and if you don't screw it up, you see a nice region, and it consists of exactly one set of iterated integrals. Remember we commented when we were doing 3 that part of the art was looking at a problem and deciding what order shall I do this in that will be optimal. So that's what that's a lesson in. And as it says in the problem, that was a test problem like 4 years ago. So you should expect me to do things like that to you.
Thanks.
You're welcome. Sir?
Can you maybe mention in passing kind of how there were ones where it was, I think, a 3D thing and we had to do like 2 separate integrals?
Yes.
The first one was like all zeros, so that was easy. But how do we do it with 2 integrals?
Well, we did one like that in class.
Okay.
That's all. I'm not going to do it. I'm not going to do it
Okay, you
anymore.
did it in class?
Okay, so, hello. So, back to where we were on Wednesday. Sorry. We were trying to decide what the average distance from a corner of the square was to points inside the square. So we wanted to know the integral over r, where r is the unit square. We wanted to know what the average value of f was, where f was the distance from the origin to points inside the square. So the distance formula says magnitude of x, or square root of x plus y squared. And so we talked a little bit at the end of class about how you would end up with some yucky integrals to do. You just did the problem. And those of you who paid attention to what was coming next, or who might, for example, have wasted 5 hours doing the wrong homework problems, already had a hint that the nature of this function makes you think, gee, maybe I'd rather use some different coordinate system. And so maybe a different coordinate system would be helpful. Certainly if I asked you to do some integral over the inside of a disk, that same thing would occur to you. If I asked you to integrate, for example, the function x squared over omega, where omega was the inside of a circle, if you set that up as iterated integrals dy dx or dx dy, it wouldn't much matter. It would be yucky. Because the region has symmetry that makes it look nice in polar coordinates, maybe it would be good to actually figure out how we can do integral problems in different coordinate systems. So we actually talked briefly about polar coordinates in the fall. Is there anybody who actually never has played with them at all, other than that? So, okay.
Well, it was like 3 years ago.
Yeah.
It was like sophomore year of high school.
But you're young, you remember everything.
No, I'm not sure.
Except for esoteric history facts that you memorized and forgot. But any math you've learned you've forgotten? I'm shocked.
when you don't use it again.
I'm shocked.
I completely forgot all the
You never even had
postulates for like
problem done?
geometry.
I'm old.
That's besides the point.
No, it's not. All right. So we can think about giving a different way of parameterizing most of the plane if we use a positive number r and a theta that doesn't wrap around too many times, and you map a point r theta here by this function g to a point xy, where, and we did write down these formulas in the fall, well, so I'm going to write it down again, where g of r theta is r cosine theta, r sine theta. And what's the meaning of this? The meaning is that r represents
Radial distance.
the distance, and then x is r cosine theta, and y is r sine theta. So an r theta here corresponds to an xy here. But in order to make it be a unique set of coordinates, so this is what Hamilton and I were debating about, if you want to have this be a unique set of coordinates, I actually will not allow what some of you were allowed in high school or when you saw this. I won't allow r to be negative.
You gotta make theta really.
So my view is, I don't want to get into confusions with saying, for this theta, negative r puts me there. I just want to say, that corresponds to a different theta. Okay? So typically, we're going to say r is positive. Why am I not allowing 0?
Because
It's just
0
a
for
break.
any theta would equal to
Right.
point.
Exactly correct. If I let r be 0, then all thetas would put me at the origin, and I wouldn't have a unique coordinate. So I'm not going to allow r to be 0. And then I'm typically going to let theta go in some interval that covers all my tracks, but according to the problem I'm using, I might not want to go from 0 to 2 pi. I might prefer to go from minus pi to pi, or something like that.
So basically that function maps from r to r minus the origin.
So it's mapping to the plane minus the origin, and I'm using some restricted interval here, like this. And how does the mapping work? Lama, are you wanting to
I
say
was just
something?
confused, it's like, how do you map the origin?
You don't.
You just don't, can't.
R equals 0 is not allowed. Sorry, so R equals 0 is not allowed here.
So G is not a linear map.
Well, it's definitely not a linear map. All right, now what is this mapping doing geometrically? If I fix an R and vary theta, what's happening?
You're going around a circle.
I'm going around a circle. If I fix a theta and vary R, what am I doing?
Going on a linear line.
No. Not a line.
Array,
It's a ray.
array with an open point at the end. Is there a term for that?
An open ray.
Open array.
Now, since we're doing integrals, you want to think about doing some integral over a region here, and you want to understand, well, what does that region come from back here? I'm not going to give any rigorous proofs today. We will do a general theorem at the end of the chapter, which covers everything that we do in the meantime. Thanks. But, for example, if I wanted to do an integral over the inside of a ball of radius A, I would then say, well, back in our theta world, I'm looking at what shape back here. If this is my omega here, what shape maps to it?
Rectangle
A rectangle that's
with a
then goes up to 2 pi, right? And to be honest, I'm going to ignore the ignore the issue with the origin. Right? I'm going to ignore this line and just say, let's pretend we're not doing the whole closed rectangle here, even though this line segment collapses to that point. It's not going to affect any integrals. All right, so the first thing we want to do is get used to what different things look like in polar coordinates, and then we want to figure out how we turn integrals into integrals. So, we've agreed that circles centered at the origin in the plane correspond to lines in r theta space given by r equals some constant. Suppose I gave you a line like x equals a. What would that look like in polar coordinates? So what, I'm going to confuse you here now, I'm going to put r theta over here just to confuse you. What in r theta would map to a vertical line x equals constant?
Is it diagonal?
So, well, first question, what does theta do here?
It
It is
increases, well,
decreasing or increasing.
That's
It's
exponentially.
It's
between negative pi over 2 and pi over 2.
Right, so here is a situation where I'd rather allow negatives just to make life easier. So I'd rather go from negative pi over 2, not inclusive, to pi over 2, not inclusive. Agreed? So the thetas over which I live are going to be this open interval of thetas. But what?
And is it?
Surely it's a curve
It's
here
kind of
that
like
you need
a
to draw.
parabola type looking thing.
It's like a semicircle.
It's not a parabola looking thing.
Well, the closest.
What's happening is you get close to pi over 2,
R's getting longer.
r is getting big. So what do you expect to see in the graph here at pi over 2 and at negative pi over 2? You expect to see asymptotes, right?
It's like,
Is it gonna be like inverse tangent?
Well, you need to use the identity for what x is.
Oh, how clever. So x equals a, but x equals r cosine theta. So you can solve for r. You were close.
I was thinking for 1 for the unit square.
And so it's the graph of secant, but just to keep you on your toes, or hanging from the rafters, one of those.
But it's plotting y to x, so that's why it's sideways.
Yes, we're thinking of theta as the independent variable and r as the dependent variable, and yet I've plotted them this way, just to mess you up. You will find out why I plotted them that way just to mess you up when we get to chapter 8.
So what does the graph look like?
What does the graph look like? What is secant of 0? 1 over cosine of 0 is 1. So we're at r equals a here, and then cosine gets smaller, secant gets bigger, and it's symmetric. Cosine is an even function, secant is an even function, so it looks approximately like that.
So it looks kind of like a sideways parabola.
But it's not no, it's not a parabola, because parabolas don't have asymptotes.
Oh yeah, you're right.
Nice try, though.
Looks
Well,
like,
you know, kind of a little bit, you know. Just if you're eyeballing it.
So notice that this region that we're integrating, that we would have, well, we aren't doing a region, it's just a curve. So never mind, yeah, okay. All right, so this curve maps to the line. And you could presumably similarly do it if it were y equals constant, you'd know what to do, right? Do the exact analogous thing. What if it were the line?
wait, so would it be the same graph?
No,
It would be.
it would be a shift of that graph to a different interval of thetas.
Between 0 and pi?
So,
That's because sine and cosine are off by a shift.
But, that's it.
so anytime x is or y is held constant, you're somehow going to get something that looks kind of like we did with.
You're going to get cosecant and then use y.
Mm-hmm. All right, now here's one that shows up all over the place in applications, as you shall see. What about a circle not centered at the origin? What about a circle of radius A centered at A0? So in my XY picture, I draw what?
Circle who just touches the origin.
Right.
Isn't it like for this one we go 0 to, we can go just go like only half the interval? Instead of 0 to 2 pi, we just go like 0, like.
Well, hang on. So again, I'm going to ask you what values of theta are represented in this curve.
Shift negative pi.
Isn't negative pi over 2 to
Could.
pi over 2?
It's again negative pi over 2 to pi over 2, right? You have thick angles that go through here. What happens at negative pi over 2 or pi over 2? It's the tangent line. Right? So if you wanted to get the whole circle, you would include negative pi over 2 and pi over 2, you'd be getting this point twice. If you leave out this point, then you go the open interval again.
Would you go open close?
You could. So it's the same game with pi over 2, negative pi over 2. I'm going to put them in there just to make life easier, even though it's not a one-to-one map. There's that one point that screws up. Now, what function do I have, though? How do we figure this out? And I'll give you a hint. You did this in homework, the first homework assignment in the course. 100. To which Jonathan's saying, you don't expect me to remember that far back.
The one
That's exactly what I was
right into the circle?
Yes.
What? It's fun.
Good guess, Gabe. Now use it. What did you prove in that homework problem?
That
Any two lines that go through a diameter.
Remember that problem?
No.
Yeah.
Yes, I remember that problem.
Yeah.
Whoever just said no better go. Well, you've been away a while, but
It was Haley.
Will, you remember? So here's theta. Here's r. In this picture, right? What equation? This is radius A. So what's the hypotenuse?
It's
2a. Whatever the max.
Oh,
are.
2a.
2a. So what trig equation can I write down here? No, way easier. You've got a right triangle. No, you've got a right triangle.
That's a J over hypotenuse, that's cosine of, yeah.
Cosine of theta equals?
R
No.
over 2a.
It's a right angled triangle. So r equals
2a cosine theta.
2a cosine theta. So what does that look like over here? Well, it's not the reciprocal there. You've got a 2a at theta equals 0, and now you've got a cosine curve with that amplitude. But you're putting it on its side, right? And of course, Llama is going to say that's another parabola, and it's not. It's a cosine curve. For those of you who hate trig, there's a less inspired way to do this. Not that I encourage you to be less inspired. What's a less inspired way to do it?
Stop being inspired.
Thank you, Dennis.
Use like
Memorize it.
back that is just shifted.
No, I'm actually not wanting to shift it. Andy suggested a shift earlier, but you'll see why I don't want to do that when we start doing applied problems here.
Can you?
How many people passed high school? How many people had to write down the Cartesian equation of a circle centered at a point with a given radius? More than you had to do that. You all had to do that. What's the Cartesian equation?
X minus a squared.
Plus x minus b squared equal to r squared.
But I'm centered at A0,
So
Right.
y squared.
squared.
and the radius is?
A squared.
Is
Write that expand that out. What's the equation?
X squared minus 2a plus a squared.
Minus 2ax.
X.
And then plus y squared equals 0.
Plus a squared.
That be the equation of an off-center circle that passes through the origin.
Oh.
Wait, could we take kind of this equation and somehow plug, like, where we kind of sub in R for, I don't know, and like plug it into another, I don't know.
Well, you can substitute x squared plus y.
So like we figured out what x equals.
Wait, am I still here?
It's kinda, no, I don't know.
Let's finish.
Okay.
Put this in polar coordinates, please.
R squared equals 2ar cosine theta.
And since r is rarely 0 on this curve,
You can divide by r.
divide through by r. There it is. Now, I actually prefer this way of thinking about it, because we're going to also do this in 3 dimensions up next Tuesday. But it might happen in homework, in web work, or on an exam that I might give you the Cartesian equation, and I want you to recognize what's going on. What would happen if this? Hmm? Oh, what's the length of r? R is the distance to the point. If you square it, it's x squared plus y squared.
Oh,
All right? And x is r cosine theta. What would happen if I put the circle on top of the
It'd be
x-axis?
sine theta.
Yeah.
It's going to switch to sine. And you can see it from the same picture. But what's different now is this is theta, right? Which means this is theta. So it becomes sine instead of cosine. Okay? And theta now goes from what to what, by the way?
0 to
Right. We're in the first and the second quadrants of theta's going to 1. Okay, so you may run into other curves in your wanders through life and through homework, but those are some standard ones. There are also curves that show up particularly nicely in polar coordinates, like the cardioid, which everybody learns about on Valentine's Day.
Over the heart. Is that R is increasing as kind of, I guess they both increase.
Dr.
I guess,
Shifrin?
one goes from pi over 2 to negative.
Hang on a sec. So that cardioid looks something like this. Actually, I'm not sure.
I guess it has like a loop.
Yeah, I thought
No, it doesn't have a loop,
Is it smooth?
but that's the question. Is it smooth there, or does it have a corner there?
If it's a cardioid, it has a corner.
Okay, what was the question?
Can you do a circle that's not touching the origin?
Much harder. So if you have neither a circle centered at the origin nor one touching the origin, most likely you're going to want to do what Andy suggested. Take the one centered at the origin and shift it to parameterize it.
Okay.
But you're going to see why the one centered at the origin, you don't want to do the shift for so many of the problems we're doing. For example, the average value question. You want to keep the origin at the origin. All right. Integrals. How do we figure out area? So what's the premise of doing integrals? The premise is that we chop regions into little rectangles. So I want to imagine taking some region here, figuring out what region it corresponds to back here. So there might be some region S back in polar coordinate space that gives me some region which I'm not drawing at all accurately, which might give me some region omega over here, and I'm interested in doing an integral back in our theta space. So this is like you did u substitutions in calculus, where you wanted to convert an x integral into a u integral over a different interval. So I'm going to imagine myself partitioning S. Remember, you could put S inside a rectangle and you would do the standard thing. So I want to take a little rectangle here, but I'm going to color code it, as you're going to see, like this. So I want to take a little rectangle and say, what does that correspond to over in this picture?
And you take the two thetas and the two lengths.
So the two yellow things are fixing theta and varying r. So here I've got r equals r1, and here I've got r equals r2. Sort of. So here I have an arc of radius r1 and an arc of radius r2. And I'm taking a piece of that where I'm between a certain theta value and a certain other theta value. So I would draw myself a certain theta value and a certain larger theta value. And those pieces that I'm drawing there correspond to here and here. Oops, it's backwards. Thanks, Cameron. So yellow is varying r. So yellow is varying r. Is that, did I do it right?
Yeah.
And green is varying theta.
Wait, were you holding a theta
I
constant?
think I had it right.
You had it right.
You had it right, yeah.
It was a question. I said, is that backward? I didn't say that is backwards.
And also my end of my region shouldn't be bumping into me either.
Now I'm confused.
Okay, talk.
I was just kidding about the color changes. Joke.
Right? Here, I'm fixing theta 1, and I'm varying r from r1 to r2. Here I'm varying theta from theta 1 to theta 2, fixing r. It's correct.
Okay.
But notice, so I've got a little rectangle here that has area. If you like, I will be more like a standard math class for a little minute and say delta r delta theta, where this distance is delta r, and this distance here is delta theta. Which should have been in green. Jonathan, be confused again. What's the area in the xy plane that corresponds to this little chunk here? It's not delta r times delta theta.
It's R1 delta theta minus R, or R2 delta theta minus
Theta over 2 pi
Can we like solve r and theta in terms of x and y?
Just
You could, but that's horrendous. Let's do the, so
sector area?
you could do sector area. What I'm going to do is say what is approximately the case, and we will do the math later to make this more rigorous, although I won't do all the proof. But look, this is a right angle, that you can check. So you could approximate this by a rectangle that has this for one length and this length flattened out for another length. So it's not exactly the same curved thing, but the areas are going to be off by very little in the limit when you take delta r and delta theta going to 0. So again, I'm not pretending I'm being rigorous here. But what's this length? It's delta r. What's this length? This green length here? It's not delta theta.
I like delta theta times 2 pi.
Theta over 2 pi times 2 pi.
No. Arc length is what in terms of angle?
It's theta times
Times radius. So this length is r delta theta, and when I flatten it out, I flatten it out into a length that is r delta theta. This length's a little longer, right? It's a bigger r. But it is still the case that I have length times width. And so, again, I will give you a proof later. I will give you a proof later that the correct thing to do when you convert the integral is to say that integrating f over the region omega in the xy plane, so I'll put an xy there just to remind you that that's in the xy plane, is the integral over s, where g of s is omega, of f of g of r theta, right? G of r theta says take a point in here, plop it over here, and you evaluate f there. And then, instead of integrating dr d theta, you do r dr d theta. And this r is coming from the fact that you need this fudge factor. And of course, I'm going to assume f is integrable.
We need fudge factor.
It's something you throw in to fudge to make it be correct. It has nothing to do with chocolate. Have you not heard of a fudge factor before? Something you throw in to correct something that isn't right? Maybe that's from the 1990s or something.
Fudge the results kind of thing.
Yeah, it's that kind of fudge.
Okay.
Yeah.
If we were gonna be rigorous, how would we find the area of that little piece? You do like
Right, you would do
big circle, nice
big-
little circle,
right,
and then
right.
something.
And you would have an error from this. It would not be exactly this. But
Delta
do you guys remember where that r comes from? Let's review. Remember derivative matrix?
Mm-hmm.
Take the derivative, oh, I've erased g. Please take the derivative of that function. What goes up? R theta. Partial with respect to r,
Go something.
Percent theta.
partial with respect to r,
Sine
Sine
theta.
theta.
partial with respect to theta,
Negative r.
R
Sine theta. R cosine theta.
abracadabraca. What's the determinant?
R.
Two
squared.
Do it correctly.
Isn't it r?
Fix it.
2r?
It's just r.
Cosine squared plus sine squared equals
1. So it's r.
Do you recall from chapter 1?
Change the part.
Well, but if you take the parallelogram spanned by two vectors, how do you find in the plane what gives this area?
Determinant.
Dot.
The determinant of the matrix with those vectors as columns. So it's not surprising that the derivative of the determinant of the derivative matrix is telling you how area is being stretched when you go from here to here by the map. And I'll talk more about that at the end of the chapter in general. Okay? All right. So we're now going to just do a whole pile of problems. Why are you okay with that? So you have to remember that when you want to take a problem, you've got to do two things. You've got to convert the region into polar, and you've got to then convert the thing you're integrating into polar, substituting into the function, but also remembering the fudge factor. And you will be so pleased to see how that fudge factor makes so many integrals easier to do than you thought they were going to be. Not all, but some. So let's go back to the average area the average length, distance from the corner of the square. So we wanted to compute for the square. We wanted to compute the square root of x squared plus y squared over that region, and then divide by the area of the square. But if I do the 1 by 1 squared, the area is 1. So I'm just going to go. So converting to polar, I've got to first of all ask myself, what region S in polar space
Well, it goes from 0 to pi.
goes from 0 to pi over 2, because r theta is 0 there, and you go around to pi over 2.
And then you can break them, it's easier breaking in half to find how R goes.
So yeah, so you might want to tell yourself
So,
that if you draw the pi over 4 line there, in the lower piece, r is being determined by hitting this line, whereas in the upper piece, r is being, just let me finish. Whereas in the upper piece, it's being determined by hitting the upper line. So you're going to have two different integrals.
Well, because it's symmetric, you only have to evaluate one of them.
Ah, so the intelligent student will say, I don't want to mess with this problem,
and stop there.
and say, this is twice the integral over half of the region by symmetry, because the region is symmetric if I reflect it across the line y equals x.
Sorry, why can't we take the integral using the whole region? Why do we have to divide it?
Say again?
Why do we have to divide up the region?
We don't have to, but Daniel is suggesting that life would be easier. So, all right, let me finish down here. Do you agree that I have to split it into two pieces? Because I have this line limiting my r when theta is less than pi over 4, and this line.
Okay. Yeah.
So I would have an x equals 1. Well, we already talked about that. That's the secant thing that's now been erased, exactly where I am. All right. So that would be this piece, like this. And then this one would be cosecant, and it's actually the mirror image. So your region S that parameterizes the whole thing is that region, and Daniel's saying, look, if I want to integrate R, it's symmetric. This region, if I flip it, is symmetric with respect to how the R's are. You can also see that directly here. Clearly, for every point here, there's a reflected point of the exact same distance, and so the integral should be the same. So by symmetry, I'm going to go with Daniel and say, let's not mess with two integrals when one would be enough. Twice the integral over the triangle of x squared plus y squared square root. Now we convert. Now, before you start anything else, convert the function. What function am I going to integrate in polar?
R.
R times
R d r d theta.
R squared.
So I'm going to have an r squared dr d theta. And now if we're just doing this piece, theta is going from what to what?
0 to pi over 4.
And for each fixed theta, what is r doing? So now you can draw that picture here, or if you feel safer, I want to make you do this a little bit, but eventually we're going to not want to be drawing 3D versions of this. We would rather just do it in this picture. For fixed theta, you shoot out a ray at constant theta, and you ask yourself, for what values of r am I in the region? I start at 0 and I go till I hit there. Here I start at 0 and I go till I hit there. knew him well, alas.
So from 0 to secant.
Oh, guess what integral we get to do?
Secant cube.
Please don't make us do this.
Oh, we're going there.
Secant
We're
cube.
too young. So this is twice the integral from 0. You can bet that at least 5 times in Weber you're going to come across this integral in this
So we
semester.
better write it down.
0 to pi over 4, integral of r squared is
R cubed over 3.
secant cubed, 1/3 secant cubed minus 0 cubed. All right. So this is an integral that I don't count on everyone's knowing how to do, so I will show you how to do it. But I won't show you the next time, or the next time, or the next time.
It's on video.
One shot.
All right, so there is some. You say to yourself, self, do I know anything whose derivative is secant cubed?
What would you like?
I know somebody whose derivative is secant squared.
Tangent.
Tangent.
So do secant squared times secant.
It's like tangent to the 3/2.
So we have
Integration by
So we have
times.
integration by
Shot
part.
in dark.
So what you really want to do is break this up and then use a trig identity. This doesn't look like it's getting you anywhere, but it's the only way I know how to do it. In some order, you're going to end up with the same thing. Secant squared is 1 plus tangent squared. So this is the integral of secant, which you did know at some point in your lives, even though you've all forgotten.
Log absolute secant plus tangent.
Right.
Oh,
And then there's this new integral. Whoops. Integral of tangent squared secant. So this is log, as Ken says, of secant plus tangent. There are ways to derive that without just having a trick. So you can write this as, so I'm not going to do this.
That's using 1 in secant like that.
I don't think so. But you can write 1 over cosine, which is what secant is, as cosine over cosine squared. Wasn't that brilliant? And then you can do cosine squared is and then substitute u equals sine theta, and you're going to have du
1 over u squared.
you're going to get du is cosine theta d theta. Oh, how neat. There's du. So I have du over 1 minus u squared.
so I didn't we should.
How do you do that?
Oh, 1 minus u squared, so.
1 minus u squared factors. And when you can factor something, you use
Partial fraction.
partial fractions.
We don't need to know how to do this, right?
You do need to know how to do partial fractions.
No, but let the something little squiggle box.
So if you do that and you do some trig identity fiddling, you end up there. But you're supposed to have that one memorized from some time. Now, how do I do tangent squared secant?
Is that the integration by parts?
Isn't the integral of one of them
Wait,
the other one? Isn't the integral of secant tangent squared? Or something?
Derivative of secant is secant tangent.
Derivative of tangent
It's
is.
secant squared.
Do you use that?
Tangent
I feel like
is
the
sine
answer
or
is
cosine,
parts.
so is that,
Yeah, I don't think that helps.
so it's not helpful to write as like sine.
You really do want to do integration by parts.
dB equals.
So which one can I integrate and which one can I differentiate?
Integrate secant tangent.
They should integrate tangent.
Integrate secant tangent, but then I would have to differentiate the other tangent. Okay, that's not so bad. All right, so what Ken is suggesting is you write tangent squared secant as tangent times tangent secant. Really don't want to spend the whole day on this, and then let this be u, and then let this be v prime. And integration by parts is integral of uv prime is uv minus the integral of u prime v. So what is u? It's tangent. What is v? What's the derivative of u, and what is the integral of tangent secant?
Secant squared.
Derivative of tangent is secant squared,
It's just secant.
and the integral of tangent secant is secant. Oh, look at that. Another secant cubed. And you say to yourself, oh no,
No, you put it on the
but it's perfect because it comes with a negative. So you get uv minus the integral of u prime v, which is secant cubed. And that's exactly the integral you wanted. You put this on this side, and you got two of them. So you divide by 2, and you get the integral of secant cubed is 1/2 log of secant plus tangent. Unfactored out by half. Plus secant tangent. So let's finish. I'm supposed to integrate from 0 to pi over 4 and then multiply by 2/3. So what's the end? 2/3 of this evaluated at pi over 4 minus this evaluated at 0. All right, what happens at pi over 4? Secant of pi over 4.
2 over 2.
Let's just say square root of 2. You guys need to get out of this 1 over root 2 equals root 2 over 2 crap and just use 1 over root 2 for the rest of your lives. Tangent of pi over 4. Secant tangent, well, we just did that. Minus this at 0. So what's secant of 0? What's tangent of 0? What's log of 1?
0.
What's, well, that's 0 too, because you're multiplying by 0. So there,
Multiple 1/2.
huh?
There's no.
Oh,
What is
that was
that?
a half.
Yes.
So it'll become 1/3.
There's the answer. If someone has a calculator, we could quickly plug it in and see numerically what that is and see if it makes sense.
It should be
I'll take your word for it.
right? Alright.
I actually did not work it out ahead, so unless somebody here has a calculator, I'm going to say that's the end for now. But
So, a question, will every graph in from 0 to, so that obviously has area 1, will it always have an area in the r theta point, or?
I don't understand.
So, we already know the area of the top one, and we found the area of the bottom one.
No. I've converted the upper integral to an integral in the other region. I don't have to think about area. I divided by the area here, and that gave me this integral to do. I don't have to think about area here. I have no idea what the area of this region is. I don't care.
Okay. Isn't that what the integral would do? No.
No, we're integrating this function. If you do the integral of r, then you're finding the area, but we're integrating r
Okay.
times
Which would be much easier. Because if you do secant squared.
Yeah, it would be easier. Okay, so next time we'll do a few more examples and then talk about cylindrical and spherical. Tuesday.